Hi everybody, I'm Andrea Bertozzi. I'm a member of the math department here at UCLA, and I have a few slides to share. I'll try to be brief. Okay, I want to start with an example. So I realize we're supposed to talk about math, but I really want to talk about applications. So this is a problem that I've been working on with Ann Andrews' group in chemistry here at UCLA, and it's regarding the selection of DNA aptamers. These are single-stranded DNA molecules, fairly short. And the problem here is really a design problem. How do you come up with seemingly random sequence of nucleotides that together in the form of a small DNA molecule will fold up in some way and then bind to a target with high affinity and specificity? And so the way this is currently done, at least using this method called systematic evolution of ligands by exponential enrichment, which is called CELX for short, is that it is literally looking for a needle in a haystack. So one creates a soup of random sequences, like billions of these things, and then over an iterative process of sort of testing them against a target, seeing what sticks, running PCR amplification on that information, and then redoing the whole experiment over again about 20 times. One down selects from about 1 billion random sequences to maybe 5,000, and that's still way too many to pick one. And so then one has to come up with a way to identify maybe a couple candidates to test in the lab. And the way this is currently done is by looking at the total count of each sequence at the end of the CELX process and looking at the high count molecules. So what we've been doing is using AI, and in particular more classical machine learning ideas, to take that data and to be able to look at, kind of sort through the secondary structure, or the secondary structures of the DNA. You can see pictures on the lower right of different configurations and how they fold up. And what you find is that, I have to take this with me, right, my leash. So for example, here's a high count aptamer from the CELX process. Here's one that just shows up one time, but it's almost identical in structure, right? And so one might ask the question, is looking only at the high count molecules the right way to do this, or do we really need to get into the weeds and start understanding a bit more about what comes out of this process? And without giving away lots of secret information, I'll just say that yes, there is something to this question, that maybe we can find molecules that we wouldn't have thought to identify by actually using some machine learning and AI to be able to understand much better the space of this problem. Now, there's a lot of nice mathematics that goes into this. So it's not a black box AI. We're actually using a fair amount of sophisticated mathematics, including ideas from subgraph matching. This similarity structure is designed using something called Motzkin paths, which come from combinatorics. So that's a combinatorial object that basically gives us a one-to-one correspondence between the shape of the DNA and the Motzkin path, and that allows us to use that as a feature vector for machine learning. And then one can actually use this for computational chemistry. So the moral of the story here is that there's a lot more to using AI than just taking black box or sort of black box language models and neural networks and just kind of plugging in things and seeing what comes out, that you can really get into the weeds and see how to use some very nice ideas from mathematics and computer science to solve some really interesting problems. So this is just one example in computational chemistry. So I want to talk about another way we can take ideas from classical mathematics to develop models for machine learning. And this is work that I've been doing for going on about 15 years now. But the idea is to take some classical ideas from surface tension, from fluid dynamics, and minimal surface problems. These are classical problems in low-dimensional Euclidean space, And all of these problems algorithmically have the Laplacian as playing a major role in the mathematics. Typically, when you want to compute these things numerically, in low-dimensional Euclidean space, when you're working with a Laplacian, one often likes to think about very fast methods, such as pseudospectral methods, where the Laplace operator diagonalizes because of the fact that the sines and the cosines are eigenfunctions of the Laplacian, right? And that allows us to use a very old idea, the fast Fourier transform, to be able to go back and forth between the frequency space and the spatial Euclidean space to be able to very quickly solve minimal surface problems. So it turns out that there's a very beautiful analogy between these things and looking at high-dimensional discrete data organized on a graph. So basically what you can do is take your data and you can put it on what's called a similarity graph, where each piece of data is a node on the graph, and then the edges between nodes describe how similar are the information on comparing between each of the nodes. So then what you can do is you can, for example, solve something like a graph min-cut problem, which is a classical problem in computer science. But we can now look at this as sort of a discrete analog of the minimal surface problem in Euclidean space. And then it turns out that all these beautiful algorithms from Euclidean space many of them have analogs in the discrete problem. So for example, we don't have the FFT, but we can try projecting onto eigensubspaces of the graph Laplacian. And in fact, because similarity graphs have so much redundancy built into them, because you're looking at, not only are you looking at the data, but you're looking at comparisons between the data in this graph structure, it turns out you don't need the full spectrum to be able to do interesting calculations. You need things like low-rank approximations or sparse approximations. That brings things like the Nystrom extension or Rayleigh-Chebyshev methods. And then we often find that we only need a small percentage of these spectral modes to be able to answer questions like the graph min-cut problem. So these methods are excellent for data reduction in training data for things like semi-supervised and unsupervised learning. They're a nice replacement for supervised neural network methods in the case where you just don't have a lot of training data. So I'm working with a team at Los Alamos National Lab right now where there's a lot of data there where we just don't have training data. It requires somebody to do some work to actually label the data. One example would be this example in the lower left-hand slide. That's a problem in surface water detection and multispectral images. Many of this information that we want to glean in terms of the surface water lives in parts of the world that are hard to get to, like the poles, right? Where it's difficult to go and make actual physical on-the-ground measurements. And the other thing is that these are mathematical ideas where you can prove a lot of theorems, but they also partner very well with modern neural network methods. One example that we've used recently in several papers is contrastive learning, SimCLR for dimension reduction of the data. So the last slide I want to talk about is another problem that is now showing up in many interesting problems, including what Damek spoke about. You mentioned the combinatorial complexity, right? I'm also just starting to work on a DARPA program, the A3ML program on anti-money laundering, where we're interested in finding patterns of activity, which is a subgraph matching problem. So what we discover is when you have a very large world space of information and you have some pattern and you're trying to find it in that space, if you can find one instance of the pattern, I claim that there's probably many, many instances of that pattern, and that finding just one instance is probably not going to answer the question you need to have answered. So most people, when they hear combinatorial complexity, if you just read the literature, you'll see that there's sort of a knee-jerk reaction that people have, which is to just walk away from that problem. But why do you have to walk away? Why not attack the combinatorial complexity problem head on? So this is something that I've been interested in, and this is some pictures from work from my group a couple years ago, published in IEEE Transactions in Network Science and Engineering. And so it turns out that you can actually make very rigorous definitions of structural similarity and subgraph matching. You can prove theorems about it. You can derive combinatorial formulas for how to count all the instances that result from making these swaps. And that allows you to be able to count, for example, we have an example with over 10 to the 100 solutions in real computational time just by taking advantage of the structural equivalence. I have an example. So now this example is very relevant for some of the talks today. This is not a mathematical proof. This is just an example from something we worked on with DARPA about 5 years ago. But the left-hand figure is a template for a problem from the biosciences related to the cytokine storm in a COVID-19 infection. And we were looking at a very large knowledge graph from lots of papers in the medical literature related to that. And we were asked, can we find any instance of this template in this giant knowledge graph? And my group was able to show that there's, I think it was something on the order of 10 to the 18 matches for this particular template. And you might think, well, how can you even begin to get your head around 10 to the 18? Well, you can, because you can actually write down a Venn diagram that shows you exactly how you map nodes in this template. P stands for a protein, for example, and then you have different colors that correspond to the different nodes on the left that give you different groups in the Venn diagram on the right. And all of this can be very nicely paired with large language models. It can be used in the same kind of way, I believe, in terms of looking for mathematical proofs, and that's something that I hope to be working on in the near future. I'll just say that much. So basically I'm going to finish by saying that there's a lot of beautiful mathematical ideas, constructs, things that we can actually get our head around and prove theorems about that are very important as pieces of solving these puzzles with AI and language models and all of the things people have talked about today. So thank you very much.